It should contain your enrollment number, full name, stream, section, roll number. Those who are already present in the class, please start giving your attendance. It should contain your enrollment number, full name, stream, section, roll number. Those who are present, finish giving your attendance and then we will start. So today we will be discussing briefly on, not briefly, the functional dependency and the normalization. We'll try to cover it with exercise, with problems. So today our class will be like this. I will be demonstrating few of the problems to you or the things that are present in this particular topic. And then I will ask you to solve problems. Okay. So today it will not be a continuous lecture. In between the lecture, we will be discussing the problems, few of the problems. Okay. So those who are already present, first give your attendance and then within 5 minutes, we will start. Your attendance will have your enrollment number, full name, stream, section, roll number. The students who are joining late, who are joining now, please give your attendance in the chat box. Your enrollment number, full name, stream, section, roll number. This must be the format. Please finish giving your attendance quickly, those who are joining late. Okay, so let us start. Now, previous day we had ended our discussion. Okay, so let us start. Now, previous day we had ended our discussion on the functional dependencies. Now, today we will be continuing that when we will be going up to normalization if time permits. And if there is a lot more time than that, then we will start our SQL. Okay. Now, see, as you have done already relational algebra, so I will assume that few of the things basics you from SQL will be easier for you to grasp. Okay. Now, this particular topic, functional dependency and normalization, this is not related to anything of your SQL or relational algebra. So this is completely different. Now, what we have discussed was, if suppose there is a table and we have suppose 3 columns. If I want to say that A is functionally determining C, A arrow C means A is functionally determining C. What it means? Whenever for a value of A, I get some value of C. If that value of A repeats itself in the table, the value of corresponding value of C will also be repeated. That is valid functional dependency. So if I take an example quickly, suppose A, X, Y, suppose this much. So 2, 3, 4, 3, and suppose 4, 7. Now in this particular table, all the values of A are unique. They are not repeating itself. And whatever is the value of C does not matter because A is not repeating itself. If suppose I have an X over here, and if A to C is a valid functional dependency, then X's corresponding value of C, that is 3, has to be repeated here, whatever be the value of B. Now, if A to C is a valid functional dependency, if it is a valid FD, that means whenever there is a value of A present in a table, the corresponding value of C will repeat itself for each existence of that particular value of A. So what we have defined as a definition or whatever you call, tuple 1 of A, tuple means what? Tuple means a row, right? If tuple 1 of A is equals to, suppose tuple 5 of A, and if A to C is a functionally valid dependency, then tuple 1 of C, whatever was the value determined here, has to be equal to tuple 5 of C. That means whenever you will get X value of A, then the corresponding C has to be equals to 3 to be a valid functional dependency from A to C. This is one point to check the validity. Now there are few more points on dependency that you must know before proceeding towards the other things that we have. Dependency does not have any order. Like if I say A to B, or if I say A to C, or if I say B to C, then only it is valid. And if I say C to B, it cannot be valid. That must not happen. So it is not an order of left to right hand position. It can also happen that your C is determining B, or C is determining A, or B is determining A. That can also happen if the corresponding values are correct, right? So this can happen. Remember this. Second one, not only always one particular one particular column value will determine another column value. It is not always that. It can be A, B together is determining C, or suppose B, C together is determining A, or suppose A, C together is determining B. These things can also be valid depending upon the values present in the table. So these 2 points you must remember. One is the functional dependency to be valid. We must have the values like this. For every repetition of your tuple, the corresponding value of that dependent variable, like C here, A to C, if A repeats itself, C will also repeat the same corresponding value. This you must remember. Point number 1. So if I give you a table and ask to check the validity of a dependency, you will be checking it like this. Next is, it is not a stringent type of dependency which will go from left to right. Left column to right column only the dependency can exist. No, right to left or any middle value to right to left, anything can happen depending upon the values, right? Like suppose if you consider, say if you consider A is your enrollment number, B is your name, and C is suppose your address, right? So I can say enrollment number is determining name, enrollment number is determining address. So A to B, A to C, all are fine. If I say B to C, name is determining address, then also it is fine. By your name only your address will be found. But again, names can be repeating itself. So name to address, you should be careful when you write. Next, if the columns are not like this, suppose C is your enrollment number. C is your enrollment number. These are just column values, right? So I can put C last, your enrollment number. Now, if it is so, for visual, visual clarity, we put enrollment number at first. Whenever we create a table, we put the primary key at first, or anything, any determinant at first. But generally, if you write it at last, then also it is not a problem. If it is C is your enrollment number, then I can write C is determining A. If A is the name, suppose B is the address, suppose C is determining B, right? I can write it like this. So the order of dependency will not matter. What matters are the values. Fine. Next is, it can also happen like this when one column cannot directly determine other. One particular column may not determine other. More than one columns can also determine others. Like suppose I don't have an enrollment number in my table. I have section, roll number, name, and address. 4 columns: section, roll number, name, and address. Now, section, roll number, name, A, B, C, 3 columns are determining the address. Suppose you have common names, you take, suppose Abhishek, common name. So, suppose CAC 3A, roll number 10 is 1 Abhishek, and CAC 3C, roll number 55 is suppose Abhishek, and then EC 3A, suppose roll number 71 is Abhishek, and double E also is having 3A, double E 3A, roll number 5 is suppose Abhishek. So there can be lot of Abhisheks. So if I say that section, roll number, and name, if I take these 3 and it is determining the address, then it can be a dependency like this. A, B, C is determining B. So this can also be a type of dependency. So it is always not this that one column will always determine other. There can be multiple columns together which is determining other. It can also happen. So these things about a dependency you must remember. Fine. Now, Next thing that we have is the validity of dependency. So suppose let us take a table A, B, C, D, E. Suppose this is a table where I have, these are suppose my values. I'm just taking few random values. C is suppose constant throughout your table. Fine. E is suppose this is your table given. It is clearly visible. I hope so. I may not draw the table out structure. It is visible. Now see, suppose you have to determine or you have to state that how many of these dependencies that I am writing are valid. Now this is not an exercise for you. This I will do it for you as a sample. Suppose BC to A. Fine. Now see, A to BC. That means whenever there is one value of A, the total value of BC, the total set of BC will repeat itself. So see here, when the value of A is A, the value of BC is 2, 3. Fine. Value of A is 2, it is A3. Fine. Now the value of A is again A. So this A is repeating itself. So whatever was the value of BC also must repeat itself. So for A, small a, the value of BC was 2, 3. Now whenever A is repeating itself, the 2, 3 value is getting repeated. Right? Every time when A is coming, the value of BC is becoming 2, 3. That means what? A to BC is valid. Fine. Next, DE to C. DE to C. DE value is 4, 5 and C value is 3. Again, DE value is 4, 5. So it is repeating itself and the value of C remains constant, that is 3. DE value is 5, 5. The value of C is 3. Fine, 5, 5 is not repeated anywhere. Again, it is 5, 6 not repeated, but the value is 3. So it means what? Whenever DE value is coming 4, 5, the value of C is 3, constant, and other values of DE column are unique. So whatever is the value of C does not matter. I can conclude that it is also valid. Next, for C to DE. For C to DE, C is a constant value, 3 all over. C is a constant value. Everywhere it is 3. That means it is repeating itself 3 times it is repeating itself. So whenever the value of C is 3, the value of DE is 4, 5, right? Next, when the value of C is 3, the value of DE is 4, 5 again. Fine, up to this is okay, it is valid. Next, when the value of C is again 3, the value of DE becomes 5, 5. So here it becomes invalid. So if the value of C is constantly 3, if the value of C is constantly 3 and the value of DE is becoming different, it was 4, 5 for the first set, it is 4, 5 for the second set also it is 4, 5, for the third set it is becoming 5, 5. So for 3 it should be always 4, 5. When it is becoming 5, 5 or 5, 6, it is becoming invalid. Okay, is it clear? How it is becoming invalid, it is clear. Okay, so some students are asking for a repetition. Okay, so first they are asking for DE to C. See, DE to C, you arrange it like this. DE value is 4, 5. DE value is 4, 5. Then DE value is 5, 5. And then DE value is 5, 6. And everywhere, the value of the right hand side, that is DE to C, so C is always 3. Now see how to check it as valid. 4, 5 is determining C, that is 3. Whenever 4, 5 is repeating itself, 4, 5 is repeating itself, but the value of C is constant, that is 3. Now when it is becoming 5, 5, 5, 5 is not repeating itself, 5, 6 is also not repeating itself in the DE column. But C is remaining constant, that is 3. So it does not matter. Only there is one repetition in DE, that is this 4, 5, and the value of C is constant, that is 3. So it is valid. Fine. Whenever your left hand side of the functional dependency is repeating itself, the right hand side corresponding will also repeat. Okay, then only it will be valid. So whenever 4, 5 is repeating itself here, 3, that was the value corresponding, is also repeating. So it is valid. Okay. Next, C to DE. C to DE. Write it like this, C to DE. C is constantly 3. DE value was 4, 5, 4, 5, 5, 5, and 5, 6. Right? So for this 3, the value of DE is 4, 5. When this 3 is repeating itself, the value of DE remains 4, 5. It is also repeating. So up to this, it is fine. Next, when this 3 is again repeating itself, this 4, 5 is not repeating. Again, here also 3 is repeating itself, but 4, 5 is not repeating. That means these two are leading the dependency to be invalid. Is it clear? Is it clear? Yes, that is the shortcut, but I'm not going into the shortcut right now. After this, when you understand this, I will tell you the shortcut. Okay, so those who remember the shortcut, fine. But for most of the people, if they are not understanding this, then they might not get the shortcut. If C is not repeating itself, but DE is repeating itself. See here, if what he is trying to say, if C is not repeating itself, but DE is repeating itself, that means it will be 4, 5 constant, right? Then if you say C to DE, if C is not repeating itself, whatever be the value of DE does not matter, because only when C is repeating itself, the left hand side is repeating itself, then only the right hand side's repetition matters. Okay. So if it is not repeating itself, then it is always valid. Okay. Now let us come to the shortcut. Okay, I have done this previous day also, but I hope few of you are not remembering it. So what is the shortcut? For any functional dependency x to y, for any functional dependency x to y, either the LHS has to be always unique in number, unique value. Either the LHS is having unique values, or the RHS must be a constant value. Either the left hand side is always having an unique value. If the left hand side is always a unique value, that means what? This case, if my left hand side is always a new value, then I don't have to bother about any repetition, right? That means what? Whatever is my right hand side, the dependency will be always valid. Please understand. If my left hand side is always unique in nature, that means it is not repeating itself. Unique means what? It is not repeating itself. It is not repeating itself, right? So if it is not repeating itself, that means what? There is no question of checking the right hand side. Whether the right hand side is repeating itself or not does not matter. If the determinant, the left hand side is called as the determinant and the right hand side is the dependent, like this. This is what your any equation is like that. So if the left hand side is always having a unique value, that means it is never repeating itself, then whatever be your right hand side's value, I don't have to check it even. I am not bothered about the right hand side. Either or, whatever be the left hand side's value, if my right hand side is always constant, then I don't have to check my left hand sides. If my right hand side is constant means right hand side is always repeating itself. That means what? Even if your left hand side is repeating itself in some instance, right hand side is always constant. So it will always be repeating itself. So left hand side be whatever, does not matter. If my right hand side is a constant value throughout the table, then it has to be a valid functional dependency. So remember this portion, this box. X to Y will always be valid if either my left hand side has got all unique values, never repeating itself, or my right hand side is always a constant value. It is not changing any time. Is it clear? It is the shortcut to determine. Every time, suppose there is a very short time given, 30 seconds, 40 seconds given for a question. So you don't have to determine whether your A is repeating, whether your B is repeating. So if this shortcut matches, always this shortcut will not match. If the shortcut matches, then it is faster for you to solve. Okay. BC2A. Okay, this one, BC2A. You tell me now, BC2A is valid or not? Tell me. BC2A is valid or not? See here, shortcuts are not applicable because BC is having values 2, 3, 8, 3, 2, 3, 2, 3, right? And A is having value A, 2, A. So shortcut is not applicable. Left hand side is neither always unique or right hand side is not constant. So shortcut is not applicable. So how I will determine? I will check for repetition. So see, 2, 3 is repeating here and 2, 3 is repeating here. So 2, 3 is giving me value of A, 2, 3 is giving me value of A, 2, 3 is giving me value of A. That means what? Whenever 2, 3 is repeating itself in BC column, A column is always giving you small a value. That means this is valid. Yes. Okay. Is it clear? Is it clear? Yes, it is valid. Fine. So I don't think there is any more questions on validity. Previously, I have shown you a slide where 2 examples were there, 2 exercises, question 1, question 2 was there. I hope now you are able to solve that. Okay. So now we will proceed towards the next thing. Next thing is what? the types of dependency. Now there are few names that we have to remember because we will be going to normalization, right? So we have to remember few names. Types of dependency. There are 4 generic types that we will remember. First one, transitive dependency. Transitive dependency. What it means? If A column determines B and B column determines C, if these two are valid, then A transitively determines C. Okay, so this is transitive dependency. If A column determines B and B column determines C, then by transitivity, A column determines C. Right? Proof, etc. you do not require right now, just the names and what they mean. This you must remember. Next one, partial dependency. Partial dependency. If, say, AB is a candidate key, but a part of AB, suppose B, a part of AB tries to determine C, where C is a non-prime attribute. Non-prime attribute means an attribute which is not a part of any candidate key. Non-prime attribute means any attribute which is not a part of your candidate key. I've told this earlier also. Not sure how many of you remember, but what is a partial dependency? If a part of a candidate key in a table, there can be multiple candidate keys, as you already know. So if a part of a candidate key tries to determine any non-prime attribute on its own, not the total candidate key, but a part of candidate key tries to determine a non-prime attribute on its own, then we call this dependency as partial. Okay, this is partial. Now these two are very important, transitive and partial. We will use this in our normal forms. Next one, trivial dependency. Trivial dependency. Trivial dependency means a dependency which is obvious. If I say AB determines A, then it is a trivial type of dependency. Suppose enrollment number comma name determines name, because enrollment number is the primary key, so anyhow it will determine every attribute. So if I say enrollment number comma name determines name, so AB is determining A, that is a trivial type of dependency. Okay, trivial means obvious. Fine. Next one, which is non-trivial, means which is not obvious but is checked by validity, that is non-trivial. Non-trivial means suppose any random dependency A to B. Okay, this I have to check the validity, and then if it is true, then I will say this is a non-trivial dependency, because A to B different columns, so I cannot say blindly that they are dependent on each other. So you have to check by column values. Yes, partial, I am repeating. If suppose there are many candidate keys, there can be many candidate keys for a particular table. If suppose AB is one candidate key, AB both column together is one candidate key. Now C is another column of that table, which is a non-prime attribute, means which is not a part of any candidate key present. Okay. If AB's part, either A or B, is trying to determine C individually, not together, like B to C, suppose, then that B to C becomes a partial dependency. B is partially trying to determine C without the help of A. Okay, so that is partial dependency. So four types of dependency that we have, and this we will use in normalization. Trivial means trivial dependency, I'm getting some queries. Trivial dependency means if suppose I say enrollment number, comma name, where I know that enrollment number is itself a key, tries to determine name. Suppose in your library, you go and say your enrollment number, then your name and all details will be fetched. If you say, even if you say enrollment number, comma name, then also same name will come. This means this is a trivial dependency. Obviously, if you give your name along with some other data, your name will come as the outcome. So this is a trivial type of dependency. And what is non-trivial? If enrollment number to name, this mapping I say, enrollment number, whether it is determining name or not, I have to check the total table, whether it is valid or not, whether enrollment number is determining the name or not, then we call it as non-trivial, where it is not obvious, but yes, it is valid, so it is determining the other column. Fine. Is it clear? 4 types are clear. Next, we have already learned the yes, all types are valid. Then only I'm saying all are valid. Next, we are already we know about the closure of attributes. Closure of attributes. Suppose quickly, if I take one example, suppose relation A, B, C, D, E, where CD is determining E, B is determining D, E is determining A, and suppose A is determining BC. Suppose I want to find the closure of BE. So BE determines BE itself. BE will trivially determine BE itself. Now see, B is determining D. So I can write B, D, E, and E is determining A. So I can write A. Fine. Up to this is okay. Next, which one are new, Sai? BE I have already used. There are no BE in the left hand side. Next, you see D. Alone D is not in the left hand side, right? Alone D is not there. A is there in the left hand side. A is determining BC, but B is already present. So I will not write B again. So B, D, E, A, C. A is determining BC. So B is already present. I will not write it again. So C I have written. Next, CD to E. C is present, D is present, and E is also present. So I will not use CD to E. So if you want, you can keep it like this, or else you can arrange it in order like A, B, C, D, E. This is the closure. Okay. So how to determine closure? By using the functional dependencies, you will go adding up values in your right hand side. So this is your functional dependency. Means attribute closure. Okay, closure of attribute can be of a single value. Suppose if I want to determine the closure of A, if I want to determine the closure of A, so A to BC, next B to D, next CD to E, right? So like how you will be determining the attribute closure. Which one you want me to repeat? The attribute closure. Some of them are writing. Can you please repeat? Which one you want to repeat? Okay. Okay. Attribute closure. See, suppose this is a relation. This is a table given. These are the columns. 5 columns. Okay. And this is the name of the table. R is the name of the table. Now there is a set of functional dependencies given. These are valid functional dependencies on this particular table. Okay. Now using this, you are finding attribute closure. What it means? Attribute closure means those attributes are finding at most how many other attributes. That is attribute closure. So if I say that what is the attribute closure of C. From this FD set, from this functional dependency set, what is the attribute closure of C? C is trivially determining C. We know the trivial dependency. Trivial means obvious. One column will determine that column itself. So C is obviously determining C. Now check the dependency list whether C is determining someone. CD is determining E, but C itself is not determining anyone. C itself is not determining anyone. This means what? There itself it closes. This is how C's closure is. We cannot proceed further without D, right? Now if I say CD closure, CD is determining CD itself. From the first dependency, CD is determining E, so I will write E here. Now see, E is determining A, so I can write C, D, E, A. Okay. Next, A is determining BC, so I can write C, D, E, A, B, C. But as C is already present, so I will not write C here. Only occurrence will be once. So what is the value of CD closure? C, D, E, A, B. You can write it in order also. A, B, C, D, E. Even if you don't write, this is also correct. This is also correct. Okay. So what is attribute closure? From the dependency set, we will try to determine whether how many attributes it can determine from the dependency. Okay. I am not coming to keys right now. You understand step by step. Okay. You may already know, but I have to go this way, right? I have to go this closure and then your equivalence, then all these things. Fine. I'm not going to keys right now. Have you understood those person who were asking me to repeat? Have you understood? যারা জিজ্ঞাসা করছিলে তারা কি বুঝতে পেরেছো? Have you understood what is attribute closure? There were 2 to 3 person who were asking me. Have you understood now? Okay. Okay, so they say they have understood. Now we will go to a different topic. Next topic, obviously this will have the idea there. It is how to determine equivalence of FD set. Equivalence of FD set. What is it? Suppose there is a relation okay, I will take the relation from the BC. A, C, D, E, H. A, B, C, D, too much we have done. Now suppose we take a relation. Now we have one functional depend FD1. On this relation, we have FD1 F as suppose F1. It has A to C, AC to D, E to AD, E to H. This is my F1. I have F2, if functional dependency set 2 on this particular relation are A to CD, E to AH. Understand the question first. I have a table named as R which has the columns A, C, D, E, H. Okay. On this, I have two functional dependency sets which are valid. One is FD1 and one is FD2. Okay. FD1 has got 4 valid functional dependencies: A to C, AC to D, E to AD, and E to H. FD2 functional dependency set 2 has got 2 valid functional dependencies: A to CD and E to AH. Okay. Now I have to check whether F1 is equals to F2. I have to check option 1. Option 2, F1 is not equals to F2. F1 can be a subset of F2. F2 can be a subset, can be a subset of F1. Okay, I have to check for the equivalence. Fine. Now, how to do this? I will be trying to check the capacity of F1 and capacity of F2 by comparing it with each other. Okay, I will be trying to check the capacity of F1 with the capacity of F2 by comparing it with each other. So how I will do? Capacity means what? Attribute closure. Okay. Now see, F1's left hand side is what? A, AC, and E. Okay. How to check the capacity of F1? I will be checking the closure of A, I will be checking the closure of AC, and I will be checking the closure of E. Right? Now, if I directly use F1 only to find out the attribute closure of A, AC, and E, obviously these FDs will be doing that. But here I have to compare F1 to F2. Right? I have to compare F1 to F2. So I will be checking the attribute closure of F1 by using F2. Understand? Left hand side of F1 closure I have written, but I will determine these closures by using the values of F2. Okay. So A closure of F2, A to CD. That means A, C, D. Okay. AC closure from F2 is A, C, and A determines CD, so D. E closure from F2, E to H, so I can write it as E, AH, then A determines CD, so this is what I can write. Okay. I am determining F1's closure. I am determining F1's closure by using F2. I am determining F1's closure by using F2. Okay. Next, similarly, I will be determining F2's closure but using F1. Okay. So by using F1, A to C, AC to D, right? E determines AD, E determines H. So E, A, D, H. Okay. Next, A determines C. So I can write E, A, C, D, H. Okay, this is what I can write. What I have done here, F2's closure I have calculated by using F1. F2's closure I have calculated by using F1. So it's a crisscross. Up to now, is it clear? Whatever I have done, is it clear? Now I will say that why I have done. Is this clear what I have done? F1's left hand side's closures I have determined, but using the FDs of F2. Okay. Similarly, F2's left hand side's closure I have done using F1. These two are fine. Now see why I have done this. See, this is what your F2 can do. Follow my cursor. This is what your F2 can do. This is your F2's capacity. Now I will compare it to the set of F1. Then only I can say whether they are equal, whether they are a subset, like that. So this one that I have encircled is the capacity of F2, right? I will tally it with the FDs of F1. These are my capacity of F1. This third bracket is my capacity of F1. Now see, A is determining ACD. First one, A is determining ACD. That means what? Here see, A is determining C, AC is determining D. That means A, I can write it here, A is determining ACD. From these two, I can write it like this. That means this one of F1 and F2 are same. The first one of F1 and F2 are same. Second one, AC is determining ACD. If I take only this one, AC is determining D. So the second one is also same. F2, I am determining these from F2. And if I compare it with F1, the second FD is giving me this AC plus is equals to ACD. Right? Next, E is determining EAHCD. EAHCD. Now here if you check these two. Here if you check these two. E to AD, E to H. And again, A in this column is this FD, A is determining C. So I can write which is equals to this. So this is also valid. So using F2, if I say F1 can be considered as a subset of F2. F1 can be considered as a subset of F2. Why? Because this is the maximum capacity. This is the maximum capacity of F2. This portion, follow my cursor. This portion is the capacity of maximum capacity of F2. And F1's all FDs of F1 is getting fitted under this. All the capacity of F1 is fitted under this. So I can write F1 is a subset of F2. Up to this is clear. This is clear. No, it is not a rule. I am trying to tally the FDs. First, I have determined what my F2 can do. This is what your F2 can do. This is what your F2 capacity, right? Now I am comparing the capacity of F2 to my F1's capacity. F1's capacity is what? These many FDs are my F1's capacity, right? Next, if all the closures of F2 that I have determined, if all the closures of F2 is covered by F1, then I can say that F1 is fitted under F2. That means F1 is a subset of F2. Okay. F2B is a subset of F1. In this case, F2 cannot be a subset of F1 because this is the thing that you have determined. This is the thing that you have determined. This you have determined using F2. That means this one is the maximum capacity of F2. And I am checking that whether my F1's all FDs of my F1 is get fitted under this F2's capacity or not. As it has proved to be yes, that all FDs of F1 is fitted under F2's capacity, so I can write F1 is a subset of F2. Okay. I have not completed yet. I have not checked in the F2. Now see the right hand side. This particular portion is what? Is my F1's capacity? Because I have determined all of them, all these closures using F1. So this right hand side is now my F1's capacity. Now I will compare these ones with the F2, whether the F1's capacity is covering F2 or not. See, A closure is giving me ACD. From F1, A closure is giving me ACD. And from F2 also, A is determining ACD. So if I write here A closure, it is giving me ACD. If I write A closure, it is giving me ACD. Right? So what I can say, the A closure of F2 is coming under the capacity of F1. The A closure of F2, that means this one, is coming under the closure of F1, that is this one I have already determined. Next one, E closure is EACDH. EACDH. Now if you take the closure of E here, E is determining AH and A is determining CD. So EAHCD, again same thing. This one is covering this one. If you take these two, F2, then the capacity of F1 is matching. So here also you can say F2 is a subset of F1. Now if this one is valid by mathematics, if F1 is a subset of F2 and F2 is a subset of F1, what it means, what these two means, F1 is equals to F2, nothing else. Understand what is the approach to solve or how you will solve. First, two FD sets will be given. I am writing here. R, a relation is given. F1 and F2 will be given. Determine the closure, the LHS closure of F1 by using F2, and determine the LHS closure of F2 by using F1. Do this. What is this one? Whatever you have got here, what is this? Capacity of F2, because you have used F2 to do this, right? So capacity of F2. And what is this? Capacity of F1. Up to this is okay. Next. So this is your step 1. This is your step 2. What will be your step? What will be your step 3? The capacity that you have got here, check with the FDs of F1 are included here or not. FDs of F1 are included in the capacity of F2 or not. FDs of F1, whatever were given as the FDs of F1, those are getting covered inside the capacity of F2 or not. Similarly, FDs of F2 are getting covered within this capacity of F2 or not. If yes, if this one, next is the decision. If this is yes, then what? F1 is a subset of F2. Because why this is F1 is a subset? Because I am checking F1 with the capacity, within the capacity of F2. F2 is maximum. So F2 is the superset. Okay. And if this is yes, then F2 is a capacity within F1. Okay. If both of them are yes, then F1 is equals to F2. If this one is a no, then F1 is not a subset of this one. If this one is no, then F2 is not a subset of F1. And if both are no, then F1 is not equals to F2. Okay. So example I have done first. Then I am telling you the rules that how to check the equivalence. Fine. How to check the equivalence. Okay. So this one I have done. Now I will give you a question that you will solve and tell me what is the answer. Okay. If one is yes and one is no, what he is saying, he or she, F2, suppose this is yes and this is no, then this will be your answer. See, this is one of the options. This was one of the options. See, this will be your answer. If both are yes, then this is your answer. If both are no, this is your answer. If one is yes, then any one of these two will be your answer. Okay. You do it with a problem, then only it will be clear to you, because this problem I have done. Now I will give you one problem. Wait, this page has reached to an end. So I will just give you one problem. I will give you 5-6 minutes, and within that you have to solve. Okay, and tell me what is your answer personally in the chat box. So question: relation on PQRS. Relation on PQRS. I have two FDs. F1 is having P to Q, Q to R, R to S. And F2 is having P to QR, R to S. ঠিক আছে? Now you will tell me that whether they are equivalent or not. If they are equivalent, then whether they are equal or they are a subset. So I'm giving you options. Option 1, F1 subset of F2. Option 2, F2 is a subset of F1. Option 3, F1 is equals to F2. Options remain same actually. You have to tell me that which one is true. And option 4, F1 is not equals to F2. Okay. So solve it and just tell me that which one is true. Okay. So I'll just give you 5-6 minutes and then we will shift to the next topic. Solve it fast. Solve it and just reply me in the chat box. Okay, within 5 minutes. After 5 minutes, I will check the answers. Okay, so I have got many answers and let's get back. See here, the correct option should be this one. Okay, now see why. Some people have also told me that F1 is equals to F2. See why that is not true. See here, P plus, Q plus and R plus you will determine, right? So P plus from here you will determine. So P, Q, R is Q. Here Q is not determining anyone alone, right? So Q will be Q only. R is determining S, so RS is fine. Here P plus and R plus you will do. So P plus is from here P, Q, R, S, done, and R to S. Okay, so these were your options. Now see, this one that you have determined is the capacity of F2. I have to check it with F1. See, F1 needs this one, Q to R. Is Q to R present here? Q plus is giving you only Q. Where is R? Q to R is not being satisfied by the capacity of F2, right? So I cannot say F1 is a subset of F2. I cannot say this because where is this? Q to R. Where is Q to R? The capacity of F2 is not covering Q to R. Understand why I am saying this is not true. Capacity of F2 is not covering Q to R. So I cannot say this. But here, this is my capacity of F1. Now this is covered here. This is also covered here. So that means what? F2 is a subset of F1. This is true because both of these are being satisfied by the capacity of F1 here. But here the problem lies, the capacity of F2 is not covering Q to R. It is covering P to Q. It is covering R to S by the closure. But Q is determining only Q. So F1 is not a subset of F2 and hence I cannot say this one is true. I cannot say this one is true. Now, if both of them, if this is also not true, then my last option would have been true. But as this is true, last option is not true. So the only option that is correct is F2 is a set of F1. Now, most of the students have given me correct answer. Those who haven't given, have you understood? Those who haven't given this answer, that F2 is a subset of F1, have you understood? Some people were writing F1 is equals to F2. Why it is not equal? Have you understood? Those who have already given me correct answers, I am not bothered with them. They have understood. But those who have not given me the correct answer, some have written F1 equals to F2. Some have written F1 is not equals to F2. These two options are not correct. Yes, finding the closure means the left hand side of one FD set F1, suppose you will determine, but using the FDs of the other FD set. Means you are testing the capacity of F2 within F1. Again, here you are testing the capacity of F1 using F2. And then you are making the comparison. Now, when you are making the comparison, Q plus, that is the capacity of F2 by the capacity of F2, Q plus is determining only Q. But in case of your F1, Q is determining R. So where it has gone? It is not covered by F2. So F1 is not a part of F2. Right? We cannot say F1 is a subset of F2. Subset means what? Subset means everything of that F1 should be covered by F2. F2 is a superset, but F2 is not giving me the coverage of Q to R. Right? Yes, only then F1 is also a subset of F2 and F2 is also a subset of F1, then only you will choose F1 equals to F2. And if F1 is not a subset of F2. F2 is not a subset of F1. Both are incorrect. Then you will choose F1 is not equals to F2. Okay. Okay, done. So this portion is done. Fine. Next, we will go to a next topic. Okay. That is named as very, very important. I am amazed to see that all students have forgot almost everything. I'm not sure about the students who are not attending the class, but those who are attending, mostly you have forgot everything. Okay, no issues. We are doing it from scratch because not only CSE, other stream students are also present. I hope you are not finding any difficulty up to now. এখন অবধি যা যা পড়ানো হয়েছে কারোর কোথাও সমস্যা নেই, I believe. And I have also jotted few of the queries on relational algebra that I will post it in your group maybe today or maybe today itself, that you need to solve and we will discuss. Okay. So relational algebra, SQL, these things require practice. These also require practice. We are doing the practice in the class only. Okay. Now, next topic that we have is canonical cover. Now, canonical cover is also named as the minimized set of FD. Minimized set of FDs on a relation or a table, whatever you call. Okay. So what is it? Suppose I have one relation and the valid FDs are okay. Now I have to check or find out the canonical cover means what? I have to check whether the given FD set is irreducible or not. Irreducible or not. That means whether there is any redundancy in the FDs given in the FD set or not. If there is any redundancy, then we will remove that. Now we will come to the point that what is a redundancy of an FD. Okay, one question I have, if there is an extra dependency in F2 after matching with all F1, then also we can say F2 is a extra dependency in F2. If you have, then F1 must be a subset of F2. F2 cannot be a subset of F1. You are having more dependencies in F2. So F2 will be the superset. F1 will be its subset. Okay. Now see, what do you mean by a redundant FD? Means the existence of that FD does not matter for the relation until and unless other FDs are present. That means if I say B to A, even if I remove B to A from the FD set, the closures that I will get will be same. There will be no problem in the closures of FD set present. So what is a redundant FD? Redundant FD means even if you remove that FD from the FD set given, it will not create any problem in the closure of any attribute present. That is the redundant FD. So I have to check whether the given FDs, any one of the given FDs are redundant or not. If they are redundant, we will then and there remove them. Okay, and see what will happen. And the final reduced set that I will get, I will call it as my canonical cover. That is the minimum FD set possible, valid FD set possible on that relation. Okay. Note down this problem. R of ABC, D. First FD, B to A. Second one is AD to BC. Third one is C to ABC. Fine. So first step, I will decompose the right hand sides of all the FDs present. I will decompose all the FDs present. See, in decomposition, only right hand side is decomposed. Left hand side decomposition is different, that we will do in the last step. Okay. Sorry, this let us take as D, or else we cannot do this. Take it as D, or else C to C is a trivial, so we cannot do it. So this is my first step. Deduce all the right hand side decomposition. Okay, left hand side decomposition is not possible like this. Like if I say, suppose I say why left hand side decomposition is not possible. Suppose I say your name and your address, sorry, name and phone number determines your address. Right, I say name comma phone number is determining your address. Now, names can be repetitive, right? So suppose I say that Abhishek and with some phone number XYZ is residing at Goriahat. And if I say Abhishek, comma, suppose ABC is residing in Birbhum. So two entities are different. So if I only say that Abhishek is determining the address, it can be a mistake. So which one? Which Abhishek? Goriahat or Birbhum? Which one? So I require number XYZ or ABC. Hence, left hand side decomposition is not possible. Like this, left hand side is not possible. Whenever I say decomposition, it is right hand side. Left hand side, how to check it? We will do it in the last step. So step 1 is decomposition of the FDs given. Okay. After this, what we will do? These ones, we will check them one by one whether they are repetitive or not. Whether without them also my work can be done or not. As simple as that. Whether their presence or absence matter or not. Okay. So step 2, we will start with the checking. Number 1, B to A. Now using all the FDs present, if I take the closure of B, BA, B is determining A, so BA. Now see, whether B is determining anyone, no. Whether A is determining anyone, AD is determining, but alone A is not determining. That means BA is still fine. So B plus B closure is only BA. Fine. Now, if you, how to check the redundancy? If you remove B to A from the FD set, then what is your value of B? see, this is your FD set. So if you keep one left hand on the B2A and look at all the others, 2, 3, 4, 5, 6, what is the closure of B? You try to find out. So try to escape, try to look over B2A and using all other FDs, try to find out what is the closure of B. Okay, tell me what is the closure of B. If you just ignore B2A, what is the closure of B? Tell me. If you just ignore B2A, what is the closure of B? Is there anything that is determined by only B? No, yes. So only B. Not possible, no, it is possible, but only B is my answer. Yes, only B is my answer. So up to this is clear. So with BA, B2A, this FD, I have, this is my closure. And if you just remove the B2A, this becomes your closure. So whatever you had using B2A, is it same if you remove B2A? No, they are not same. This means what? If you remove B2A, your functional dependencies will not remain the same. If you remove B2A, the functional dependency, the capacity of the functional dependency will not be same. So after this step, we will say, so B2A is an essential FD. B2A is an essential FD, not redundant. So how to check whether an FD is redundant or not? This is the step. First, including that FD, using all other FD, you determine the closure. Then you ignore that particular FD and try to determine the closure, same closure, by using other present FDs. If the value of the closures remains same, using that and ignoring that, both are same, that means the existence of that particular FD doesn't even matter. Without that also I can do everything. Then only I will call it as redundant. But in this case, if you remove B2A, the closure of B is hampered. Other FDs are not giving you B2A. This means B2A is essential. It is not redundant. And hence, we cannot remove that from my set. So it is reducible dependency we are trying to find, right? So whichever are redundant, we will remove them. This is not redundant, so we will not remove this. Okay? Like this, we will be doing for rest 5. Why should we remove B2A? Why not other value? I am not removing B2A. B2A, I am trying to determine whether B2A is redundant or not. How to do that? First, using B2A, including B2A, all other FTs, I am determining closure of B. After I do that, then I ignore B2A. Using other FDs, I try to determine the closure of B. If after ignoring also the closure of B remains same, then I will say it is redundant, because without it also I can perform the same thing, right? But here in this case, B closure is not giving me BA. That is, it is not same. That means I cannot remove that. It is essential. Others cannot perform its work. Have you understood? Have you understood this step? Then I will go forward with the other steps. Means with the other FDs. Have you understood? I have got only one yes. So more than 500 students are doing the class and only one yes. Okay, now I have got some of the yes. Fine. So now I will show you that which one is repeatable, which one is redundant. Now let us take number 2. Number 2 is, let me see which one is AD to B and AD to C. AD to B. Okay. Now, including this, let me just, so AD to B. Next, anything else? See here. AD to B I have used. AD to C is also present. I will use all the FDs, right, to determine the closure. So AD to C is also present. So this is what I can write. Okay. You can write it also in order. It does not matter, as I have told. Now, ignore. Use other FDs and find out AD plus. Use the other FDs. So only this one is, only this one is ignored. See others, this one, this one, this one, this one, this one. You can use any one of them. So AD to C is there. So I can write it here. AD to C. Anything else? C to A is already present. C to B is present. So I can write it here. B, right? So already A, B, C, D all is covered. So I'm not writing anything else. Now you see, even if you ignore this one, the one that you have got and now whatever you are getting are same. Now you understand what is a redundant FD. AD to B, this is an FD present. Now, by using AD to B, I am getting AD to B and B to C, AD to C. So I am writing ADBC. Now, if you ignore AD to B, because I have to check whether it is redundant or not, I am ignoring AD to B and I am using other FDs to find out AD closure. If you do this, I have AD to C and I have C to B. Using them, I am getting ABCD. So even if I am ignoring AD to B, I am getting ABCD. So with this and without this, my AB closure is same. With this and without this, my closure remains same. So what can I say? AD to B is redundant and we will remove it. Remove it means now only we will remove. For the other FDs, we will not use this. So just remove. Number 2 is removed. Have you understood? Have you understood? First, take one FD, take its closure. So AD to B is my FD. Using all FDs, I am taking AD's closure. So it is ABCD. Fine, using all FDs. Now you reduce AD to B. Now you consider AD to, you ignore AD to B. Fine, you take other FDs, but you consider only AD to B. Then what you are getting? You have AD to C, one FD, and you have C to B. So using them, you are getting again ABCD. So even if you are using this particular FD, and even if you are not using, you are ignoring this FD, your result becomes same. That means what? If you keep this FD or you don't keep this FD, your answer remains same. Okay? So this is the case where we call it as redundant and we remove it then and there. We remove it then and there. For other FD checkings, we will not use it. Okay? Now we will take AD to C. Number 3. AD to C. AD to C, C to B you have. So what you have got? A, B, C, D. Now ignoring AD to C, if you take AD's closure, if you ignore AD to C, if you ignore AD to C, then AD's closure, A is not determining anyone, D is not determining anyone. So AD's closure remains as AD only. If you ignore this AD to C, if you ignore this AD to C, then A is not determining anyone, D is not determining anyone. So it is only AD. So these two are not same. So this one is essential. We cannot remove this. Right? So number 3 is also essential. Now number 4. See number 4. C to A, then C to B, C to D. So I'll just write it quickly. C to A, C to B, and C to D. So this one, C closure is CA, right? Now CA is giving you anything else? C is giving you CA we are using. So C is giving you B, C is giving you D as well. So you can write that. So again you have got ABCD. Now you ignoring C to A. C to A if you ignore, then C to B, C to D, and B to A you have. See here, you are ignoring this one. So C to B you have, C to D you have. Now B to A also you have. This was not redundant. So B to A you also you have. So how I am getting this? C to B, C to D, and B to A, right? So I'm getting A, B, C, D again. So with this and ignoring this, these two are becoming same. That means this one is redundant. Okay? So redundant means what? Then and there I have to remove. Just remove it. Okay? Next one, number 5. C closure is C to B, C to D. C to A I don't have anymore. Now B to A I have. Right? Now if you ignoring C to B, C closure, B you have ignored. So C to D. If you ignore B, now you are ignoring this one. So what remains? C to D only remains, and AD to C and B to A. So C to D only remains. This means you are getting CD. So these two not same. That means this one is essential. Right? Next, this one, last one. C closure, C to D, right? Ignoring, sorry, C to D, and this one is also essential. So C to B and B to A. Sorry, I just forgot. Which ones I am using? C to D, C to B, B to A, right? Now ignoring this one, what you will get? C to B and B to A. So you will get ABC. D is not here. D is not present. So this one and this one not same. That means C to D is essential, right? Yes. Okay. Step 4. Step 4. Yes, what is the problem in step 4? C to A I have. So C closure, if I take, I get ABCD. Fine. Now if I ignore C to A, I get C plus S, C, B, C to D. Now B to A is also present. So ABCD again I get. Hence it is becoming redundant. Okay. Step 5. AD to B is already removed. Yes, I'm not using AD to B. Where I have used AD to B. Step 5. C to B. So I have got C closure. I have got C to B, C to D, and B to A. Fine. Now if you remove C to B, then only C to D remains. Nothing else. So C to D. Fine. So it becomes essential. What is the problem in step 5? No, which are removed that cannot be used again. Then and there I am removing. You see that whenever you are getting a redundancy, then and there I am removing. So after this, one student has given attendance at this point of time 3 times. So it does not make any sense. Anyway, you will get absent. So no need to give attendance. So if you get one redundant value, then you remove it then and there. Okay. AD to B I have used. Where I have used AD to B? I don't think I have used it again. Where I have used, can you tell me? In step 3, I am using AD to C. Where do you see AD to B? AD to C, if I do, then AD to B, if I have, AD to C, if I have, then AD to C, then C to B. AD to B I have not used. C to B I have used. Step 2, so I will use AD to B because there only I have used AD to B and there I have removed it. I have proved it is redundant and I have removed it. After that, do you see any point where I have used AD to B? I don't think so. After step 2, only I have understood that this is redundant. So I have removed. After that, did I use AD to B anywhere? No. Anyway, so which ones are essential then? B to A. So let me just write it now. Essential, this is your step 3. Essential FDs. Which ones are? B to A, AD to C. Then let me check. C to B, C to D. C to B, C to D. Okay. These are essential ones. Fine. If you are present from the beginning of the meeting, then why you are giving your attendance right now? You have already given. Now, this becomes your essential FDs. Now you see C to B and C to D are present. So we will use a rule. I am telling the rules after this. C to BD. So if left hand side is same, right hand side you can combine. Fine. So this becomes your essential set. Now, AD to C, here your LHS is having A and D, two attributes. So in step 4, I have to check for the LHS, right? So I don't have a problem with B to A, I don't have a problem with C to BD. So I will check for AD to C. How I will check? How I will check this? AD's closure I will take. So using this, I will take AD's closure. So AD to C and C to B you have. So A, B, C, D. Now, A individually and D individually, right? So A individually, if you take, you get only A because A is not using anything. A is not determining anyone. So only A. And what about D? D is also not alone determining anyone, right? So this, that means if you have AD to C and if you have only A and only D, they are not determining this one. They are not determining this one. That means AD to C is essential. Okay, means AD to C is not essential. A and D both are essential on the left hand side. So how to check whether they are more than one variable? How to check whether both variables are essential or not? First, you take the closure of both variables together. Like AD closure I have taken. Next, you take the variables or you take the attributes one by one. From the left hand side, you take the variables one by one, take their closure and check whether the closure of the single attribute can come up with the ultimate value or not. That is ABCD. Okay. If you have AD to C, you take AD's closure, then you break that AD into A closure and D closure, right? If A closure and D closure individually is also capable of offering whatever AD closure is offering you, then you can just decompose AD closure. Okay, but here it is not possible. A closure is giving you only A, D closure is giving you only D. So the decomposition is not possible. Okay. I hope this is okay. Now, so what is your canonical cover or reducible set of canonical cover or minimal FD set or irreducible FD set? Okay, B to A, AD to C, C to BD. I hope so. BD. Yes. Okay, so this is your answer. Fine. So step 2 is a bit big. You have to go one by one. Okay. Okay, step 4. People are asking for step 4. Just once more. Step 4 is if you have any FD where your left hand side is more than one attribute. Okay, left hand side is more than one attribute. There, how you will check? First, take the left hand side totals closure, AD's closure. You find out something, right? Then you break up them into single variables like A closure, D closure. Then you try to find out the attribute closure using your FD set, this one, not the first one now, this one, because this is the latest one. If the single variable's closure is able to give you whatever your actual closure, that is ABCD, if this is giving you ABCD, then A closure is enough. I don't require AD closure, right? So you can remove D. But here it is only giving you A, not ABCD, right? So A closure is not same as AD closure. Similar for D closure is not same as AD closure. That means I have to keep AD closure. I have to keep AD to C. I cannot break it into A or D. It is not possible. Okay. No, we will not remove the FD. If the closure is same, we will not remove the FD. Suppose A closure is giving you A, B, C, D. Then I will write A to C. I will not write AD to C. Okay, D I can remove. If A can enough do what AD is doing, then D I can remove. Is it clear? Is it clear to everyone how to determine the canonical closure? Okay, I hope it is clear. Okay. Now I will just give you one exercise. V, W, X, Y, Z. Okay. V to W, V, W to X, Y to V, X. Canonical cover. Okay. Find out the canonical cover. So what you will do? Finally, you will tell me that which dependency you are removing. Okay, finally you will tell me that which dependency you are removing. Okay, so solve this and tell me that whether there is any redundancy. If it is there, then how we will be covered, or how we will be ignoring that. Okay, just wait for a second. This should be VW to XZ. Sorry, this should be VW to XZ. Fine, just do it and tell me whether you can remove anyone or not. So A and D individually is enough. Then what we have to do? A and D individually is, if it is enough, suppose A is individually enough, then you remove D. If D is individually enough, then remove A. First you take this problem, then I am scrolling up. First you take this problem, then I am scrolling up. Okay. I hope you have noted the problem. Okay. So once I start getting answer from majority of the students, then I will start discussing. Okay. So I hope you have taken the problem. So they are asking me to scroll up. So I'll just scroll up from the beginning. Okay. Beginning of this problem. So this was your problem. This was the problem. Step 1 is decomposition of the right hand side. Step 2 is starting to check whether you have any redundancy or not. Each one you have to take and check whether they are redundant or not. How to do that? I have repeated several times. Next, whatever you have got redundant, you just remove them, right, and form a step. And last step is, if there is any composed LHS, then you just check that. Okay. And finally, you get the canonical cover or minimum FT set or irreducible FT set. Fine. And this is your problem. So solve it. Okay, so solve it and take a 5 minutes of break. So we'll just join back within 10 minutes. Okay, so I'm just giving you 5 minutes to solve and 5 minutes for a break like that. And after that, I'll check the chat box and find out that what is your answer. Fine. So people who are present in the meeting may not leave, because if you leave, then your attendance will be hampered. Okay, so be present.
Recording stopped. Recording in progress.
Okay, so I have got a lot of answers. Now let us resume back. Yes, so many answers I have got. Now, let me just do a tick. V to W, is it redundant? V to W, say yes or no. People who are writing answers, V to W is not redundant, right? Okay, so this is valid. This is essential. Fine. Now, VW to X. This will be reduced to VW to X, means decomposed. VW to Y. VW to X is valid. It is essential. VW to X, is it essential? Yes. VW to X is essential. Fine. VW to Y, is it essential? VW to Y, is it essential? VW to Y, is it essential? Sorry, Z, sorry, VW to Z, sorry. Is it essential? Yes, essential. Fine. Next, this one. Tell me which one is redundant. Which one is redundant? Now tell me among these three, which one is redundant? Right. So this one is redundant. This one is redundant. That means fine. So my reduced set is right. So this becomes my reduced set. Okay. Now have you checked for VW? VW to XZ. Have you checked for VW to XZ? Can only V do the work or only W do the work? Can only V do the work or only W do the work? Only V can do the work. VW closure is what? VW XZ. Right? If I take only V, VW is coming, it is doing XZ. Right? If I take only V, then if you take only V, students who are saying V closure is equals to VW XZ, students who are saying this, I am decomposing VW into V and W. I'm not telling V determines XZ. I'm not saying this determines XZ. So for the time being, only this one and this one will work. VW and Y to V. Only these two you will use to determine V closure. So is this giving you VW XZ? No, it is not giving. So V and W both are essential. Right? How can you remove W? Understand the problem. VW together is determining VW, X and Z. Fine. Now VW only we are decomposing into V closure and W closure. At that time, VW to XZ is not existing. Understand? VW to XZ is not existing if you are breaking this up and using this. Right? VW to XZ you have to ignore, and then only you can identify V closure and W closure. Understanding my point? VW to XZ if you keep, and then also you have to identify V closure and W closure, then always the answer will come as yes. No, it is not like that. You have to ignore VW to XZ, and with other dependencies you have to check V and W can do the work or not. Right? So if you have this, if you write V to XZ, if you have V to W, if you have V to XZ, and if you have Y to V, if you have this, you are saying that you will eliminate W, right? So if you do this, right? So if you do this, then it will not be same, because if you have VW to XZ, if you have this one, then only this one is determining XZ, right? Only V is not determining XZ in this case. If using other dependencies, suppose you had W to XZ and you have VW to XZ, then you can say that without V also I can work, right? Or if you have V to X, suppose, and V to Z, then using these two also you cannot combine because left hand side is not same, right? So if you have other dependencies which will be equal in determining V closure and give you this one, then only you can remove W, or else you cannot remove W. Okay, so people who are saying that I can remove W, no, you cannot remove W just like that. You should have other dependencies by which you should be able to identify V closure equals to VW exit, but that is not possible in this case. AB to CD, AB to CD is redundant. I'm not getting the thing. Closure of V, if you identify the closure of V, then VW is the closure. W is not determining exit. If W was determining exit, then you could have written it here and then you can ignore VW to VW exit, right? You have an only V to W. W to exit you don't have. So how can you say that you can eliminate W? Okay, so one student is saying that Y to X is coming as essential. Y to X is coming as essential. And some are saying that Y to X is not coming as essential. It is coming as redundant. Vx to Vw to Xz you have to ignore, or else how can you get there? If you include that, you will always get Xz, and then only you can say that Vw is redundant. If W was determining Xz, then only you can put that yes, V is determining W, W is determining Xz, so I can say, right? Now tell me, what about y to x? Some students are saying that, only one student have told me that y to x is essential. So why others are saying that is redundant? Y to x is essential or redundant? Tell me first. Essential or redundant? Y to x? Most are saying redundant. Now I have to solve them. Some are saying essential as well. Y to x. Y to x. Most students are saying redundant. Only 1 or 2, 3 students are saying they are essential. Okay, let me do this. If you ignore y to x and you try to take y's closure, if you have y to x, then y v x z, y v x z, and v to w, so I have w as well, right? Now ignoring y to x, ignoring y to x, y to x, if you ignore y to v, y to z, y to v, y to z, v to w you have, right? V to w you have. Next, vw to xz, vw to xz also you have. So vw, if you have x. So see, these two are the same. So why you are saying it is essential? It is redundant. Students who are saying it is redundant, essential. Why it is essential? It is redundant. যারা essential বলছো, those students who are saying this as essential, why they are essential? I am finding it as redundant. Why w is included? Because v to w I have, v to w আছে তো, I have v to w, so w is included, and then vw to x. Understood? W is included because v to w I have. See, v to w আছে তো, v to w, so then vw to x, right? Okay, so I'm closing this one now, and now we will go to finding out the keys and number of keys. Okay, now see, this is done. Fine, so I'm not taking up more questions on this. Now see, R of A, B, C, D. Here I have, suppose, A to B, C, C to D. That's it, suppose. Now, if I take A's closure, A, B, C, C to D, right? So A, B, C, D is what? Total relation R. R is having how many columns? A, B, C, D. And A closure is giving me A, B, C, D. So A closure is equals to R. That means A is a key. Which key I am not telling. Only key. This means what? Key's closure has to be equals to R. Okay. Suppose you take BC. BC. So BC is giving you BC. BC is giving you D. ABCD it is not giving, right? So it is not equals to R. So BC is not a key. BC is not a key, right? So this I should remember. Key's closure must be equals to R. Okay, key's closure must be equals to R. Next, 3 things: prime, attribute, non-prime attribute, essential attribute. Prime attribute means part of candidate key, not a part of any candidate key. And what is essential attribute? Which does not remain in the RHS of any FP. Okay, so what is essential attribute? Which cannot be determined by any other attribute. What is essential attribute? Essential. I'm coming to CK and PK. Understand step by step. Essential attribute means those attributes which cannot be determined by anyone else. Okay, that means which are not belonging to the right hand side of any of your keys. Okay, that is essential attribute. Fine, up to this is okay. And whenever we are trying to find out key of a relation, remember the closure of the key. The closure of the key has to be equals to R. Okay, has to be equals to R. Now, next, now we will come to the concept of super key, candidate key, and primary key. Though we have understood it theoretically, suppose R of ABCD, ABC to D, AB to CD, A to BCD. Okay. A closure equals to, fine. AB closure equals to, ABC closure equals to, ABCD closure equals to, trivially. So all are keys. So if I write set of super keys, fine. Now, I'm coming to essential, non-essential later. Right now, understand. Have you understood up to this? Based on these FDs, I have determined 4 super keys. Okay. Now, what is a candidate key? Any proper subset of a candidate key cannot be a super key. Let me write. Any proper subset of a candidate key is a super key. What is a super key? Any key. Any key is a super key. That means any number of attributes which is able to determine other attributes are super key. Okay. So here from this set, A cannot have any proper subset. Any proper subset of A is null. So A is a candidate key. A cannot be having any proper subset. The proper subset of A is null, right? So that cannot be a super key. So A is a candidate key. AB. AB can have proper subset like A and B. As A is a candidate key or a super key, so AB cannot be a candidate key. No proper subset. No proper subset of a candidate key is a super key. No proper subset of a candidate key is a super key. Okay. Next, ABC. ABC has got A in it. So a proper subset will be A, and A is a super key. So ABC cannot be a candidate key. ABCD, again A, so it cannot be a candidate key. Now this means among these four, only A, single A is a candidate key. Fine. Now take other variables. Suppose BC. Suppose BCD. Other than A. Suppose CD. Suppose B closure. Suppose C closure. Suppose D closure. Look at this one. On your left hand side, only B, only C, only BC, nothing is present. That means what? They are not able to determine anything else. So BC only, BCD only, D only, C only, B only, CD only. Right? If you take BD also, then also same thing. So no one of them is determining R. R is ABCD. So no one of them is determining R. That means none of them are super key or candidate key, nothing. First, it has to be super key. Then only it can be promoted to candidate key. Okay, based on that no proper subset. So none of them are equals to R. Now say why. Why? Because look at the relationship set. See, on your right hand side, you have A, you have B, you have C, you have D, but you do not have A. You don't have A on your right hand side. You don't have A on your right hand side. That means A is an essential attribute here. A is an essential attribute in this relation. A is not present in any one of your right hand side. So A is an essential attribute here. Hence, whenever you determine a key, it must have A in it. Whenever you determine a key, it must have A in it. Suppose you have this one, you change it to AD. AD determines A itself and D itself, and C, A is determining BCD. So BC also will come. That means ABCD. That means equals to R. That means AD can be a super key. It cannot be a candidate key because it can be reduced to A. So it cannot be a candidate key. A is the candidate key, but AD is a super key. So the first and foremost rule of determining a key from a relation is identify the essential attributes. Essential attributes must be a part of a key. Any key you determine, be it a candidate, be it a super, be it a primary, anything you determine, essential attribute must be a part of it, because essential attribute is not able to be defined by anyone else. Essential attribute is not present in any of the FD's right hand side, right? So essential attribute must be present in the key itself so that it trivially determines itself. Like this, AD determines AD itself trivially, right? So essential attribute must be present in your key. Okay, this is the first point. Essential attribute you have to determine, find out, right? Second, find super keys. Third, identify minimal super key as candidate key. Now, one student was asking me, what is the primary key? Any one. In bracket, we must say the easiest one to use of the candidate key is primary key. Suppose I have primary keys like, suppose for example, I have candidate keys like, candidate key 1 is enrollment number of a student. Candidate key 2 is name, comma, section, roll number. This is a candidate key. Number 3, suppose name, comma, phone number. Right. So if these 3 candidate keys are present for one table, which one is easiest to use? The one which is smallest. So enrollment number will be your primary key. Okay. And all of them are super keys. Remember, all of them are super keys, and other than these, there can be other super keys as well. Okay. Up to now, whatever I have told about keys, is it clear to everyone? Essential attribute, prime attribute, these things are clear. Scroll up here. I will do problems so that it becomes all essential attributes are candidate keys. No, only essential attribute cannot be a candidate key, but other than means along with essential attribute, there can be other attributes also in the candidate key. But essential attribute must be present in any key. That can be candidate, that can be super, anyone. Okay. Now, next one is finding out the number of candidate keys in a relation. Suppose first step, essential attribute is, which one is the essential attribute? Which one is the essential attribute? D. So D must be present in your key. Now they have asked for candidate key. Okay, so we will try to keep it minimal. Now AD, BD, CD. Minimal. Fine, because A closure, essential attribute must be present. Because why? A closure can give me ABC. B closure can give me ABC. C closure can give me ABC. But no one can give me R. No one can give me R. Right? So D must be present. So minimal set AD, BD, CD. Now, A is giving you B, B is giving you C, C is giving you back A, and D is present. That is equals to R. B is giving you C, C is giving you A is giving, and BD is giving you D. Next, CD is giving you A is giving you B, and CD is giving you D, so R. So these three are minimal set. These cannot be reduced. D alone cannot determine anything, only D. Okay, so that is not equals to R. D is not determining R. So these cannot be reduced. That means these are my candidate keys. Now I will try to add on variables if possible. Now see, if you add, AD is present, so if you add B, or if you add, suppose C, that means what? Already BD is a subset, already CD is a subset. So they cannot be candidate key. Yes, they are super keys. but they cannot be candidate key. Why? Because this one is a subset, which is already proved to be a candidate key, right? So no proper subset should be a candidate key. That means this should be a super key, but this cannot be a candidate. Is it clear? Am I making myself clear? First, you find out the essential attribute. Then you add one variable each to the essential attribute and try to find out whether it is giving you R or not. If it is giving you R, well and fine, that is a candidate key. Now, if it is not giving you R, then you have to go on adding variables. But if it gives you R and then also you add variables, then it will not be a candidate key. It can be a super key. Even ABCD is a super key. Yes, ABCD is also super key. ABCD trivially determines ABCD itself. So it is a super key, obviously. Okay. So how many number of candidate keys? 3. Okay. How many number of candidate keys? 3. Fine. Suppose next one. Problem number 2, suppose. Tell me number of candidate keys. Tell me number of candidate keys in the chat box. Solve this and tell me the number of candidate keys in the chat box. What is the primary key in the problem? Those all of the trees, every one of them were having 2 attributes, right? So anyone you can pick. That depends upon the database administrator, DBA, anyone you can pick. Okay, generally we go for the smallest, but as all of them are having 2 attributes each, so you can pick anyone. Okay, so do this problem and tell me what is the number of candidate key. Tell me what is the number of candidate key. I have got 3 answers. One student is saying 2, one is saying 3, one is saying 4. Okay. B is the essential attribute. So AB, BC, BD, BE. I will try with them first. AB is giving me ABCD, BC is giving me D. So R. So this becomes my first candidate key. Next BC. BC is giving me DE and D is giving me A. So R. Fine. Next. BD, BD, A. AB is giving me CD and BC is giving me E. Right? So third. Next, BE. B is giving me what? Nothing, only BE. Right? Now, next, with BE, if I add A, then AB is already a key, so it cannot be a candidate key. With BE, if I add C, then BC already done, so it cannot be a candidate key. With BE, if I add D, then it cannot be a candidate key. That means how many candidate keys? How many candidate keys? 3. Okay, candidate key must have the essential attribute. Essential attribute is B. So B must be present. Now if you say that if I do C, D, E, then C, can C, D, E determine B? No. So B must be present. Essential attribute is that one which is not present on the right hand side of any FD. Okay, so you have to include that essential attribute into your key. That key can be primary key, that can be candidate key, that can be super key, anything. Okay, and what is your candidature for a candidate key? No proper subset of a candidate key can be a super key. Okay, that means here if you have DE, B is not a candidate key. So if you add variable, then you see that already made candidate keys are coming into that variable. So we will not do that and we will stick to our candidate key, that is 3. Okay. Now just do a last one. CE to D, C to A, D to B. Last problem, tell me the number of candidate keys. See the problem here? Your essential attributes are C and E, right? So C and E both must be present in your candidate key. C and E both must be present in your candidate key. Now, if I take only CE closure, both must be present. So both I have taken. CE is determining CE itself, right? CE is determining D here. So C is determining D, D is determining B here. So D is determining B. Now C is determining A as well. So C is determining A. That means it is giving me R. So CE is my candidate key. Now understand, few people are writing 3, few are writing 5 and so on. But understand, whatever I have essential attributes, I can add variables in them. Right? I cannot take only C and add A. I can only take C and add B. That will not make a key. I have to take CE and then only I have to go on adding variables. But if I go on adding variables, that will make them as super keys, not candidate keys. So candidate key is only one, that is CE, right? Candidate key is only one, CED. One student is saying CED. How CED can be a candidate key? The proper subset of CED. What you are trying to say, CED. CE is a proper subset of CED, right? CE is a proper subset of CED. So CE is a candidate key. So how can CED be a candidate key? It can be a super key. It cannot be a candidate key, right? Why E is essential? Because E is not present on the right hand side. Check the functional dependency set. This is your functional dependency set. See, C is all, A, B, D is present. So A, B, D is present. C, D is not present. Right? Is it clear? Only one candidate key. Only one candidate key. Okay. Now, next is, today I must end it here because there is only hardly 10 minutes left, and within that new topic of normalization cannot be started. But so just to give you very brief introduction about normalization, very brief introduction about normalization. See, in a database, in a table, in a particular table, we have different rows and columns, right? We have different rows and columns. Now, the values that we have in different rows and columns, if the values repeat themselves, suppose I have a table where I have student ID, student name, branch code, branch name, and HOD name. Okay. Suppose student ID is my primary key, or just the identifier, whatever you say. Names are different only. I am just taking it like that. Now see, student ABC, all are studying in CS branch with HOD name X. Fine. This person is, suppose there is another student. These two persons are studying in, suppose, ECE branch, where the HOD is, suppose, Y. Okay, and this is, suppose, 104. This is, suppose, biotech branch. And okay, now see, you can see there are repetitions of data. If you maintain, what is the problem? If you try to maintain data in a single table, this is a single table which is having student data also and branches data also. You are trying to map student with branch, right? So if you try to maintain a data like this, then there can be few problems. The first problem is, suppose you want to insert a student, a student comes and wants to take the admission where the branch is mechanical. Suppose electrical branch, someone wants to take the admission, but here how you will insert that person? I have to insert the student ID and student name with respect to branch, right? So electrical branch is not existing here. This means what? Suppose in your college, in UEM, you have CS, EC, EE, triple is not there right now. Civil, mechanical, biotech, right? So suppose there is no student presently uh, studying in civil and mechanical. Suppose that means what? The department is obsolete? No, department is present, but right now no students have taken admission. That does not mean in future also, in the coming 1 or 2 months also, no one will come and take admission, right? So if this is the situation where depending upon some other value, I cannot insert a new value, we call that problem as insertion anomaly. Why this is anomaly? Why this is not a problem? Because problem is something that occurs in every situation. And anomaly is something which is a rare case, may or may not happen. Suppose a student comes and wants to take admission in CS branch. Then I don't have a problem with this table. I will say that insert this student where branch code is 101 and branch name is CS. So that person will be just inside the table. But what if I have a branch civil, mechanical, electrical, which is not having existence in the table? I cannot insert. So this is named as insertion anomaly. Next one, deletion anomaly. Next one, deletion anomaly. What is it? Suppose student F has left UEM, left the college. So if I want to delete student F, the information about the branch of biotech is also getting deleted. The total row will get deleted, right? So biotech, only one existence of biotech was present. So that will also get deleted. But this must not happen. If a student is leaving a college, should the department just comes to a shutdown? No. But this is happening in this table. So that is named as deletion anomaly. Along with some data, if some other set of data which is existing hardly is getting deleted, we call it as deletion anomaly. Okay. Next one is updation anomaly. Updation anomaly. Suppose I have a branch as CS and the HOD name is X. Suppose now X has to be replaced by Z. X has to be replaced by Z. Now, if you can do it by the code, suppose wherever code is 101, my HOD name should be Z. Then it is okay. Everywhere it will be replaced. But if you just do it like this, where my student ID is 1, replace that, student ID 2, replace the student ID 3. If you do it manually, then at some point, maybe suppose 100 data is present, 1 or 2 data remains unchanged, unaltered. Then what will happen? CS has got HOD existence as X somewhere and Z somewhere. Then it is this type of problem is named as updation anomaly. Okay, so you can see if you maintain all the data in a same table, then these type of problems happen. 3 types of problem generally we identify. We call them as insertion anomaly, deletion anomaly, and updation anomaly. Okay, and what we do to get rid of this, we maintain 2 tables, more than 1 table, where here I maintain student ID, student name mapped with branch code, and here I have my branch code, branch name, and HOD. Okay, so here 101 will exist only 1, 103, 104, and so on. But here I can have 1, 2, 3, 4, 5, 6. Here I can have more than 1 existence of my branch code. The thing that is named as the primary key of one table acting as the foreign key of other table. Okay, so what we do, we divide table. We divide tables in order to organize the data well. This is what we do. Okay, and this division is named as normalization. So from here we will continue next day. This is named as normalization. So why do we opt for normalization? Because we have these type of problems. So what we do, we simplify the tables, we make the tables into like we divide the tables into sub tables, and where one table's primary key can act as the foreign key of the other table. Okay, so we have different normal forms. First normal form, second, third, BCNF, 4 normal form, 5 normal form. So we will study everyone with examples, and we will also see that when exactly we have to break, what type of dependency if persisting in my table, then only I will break, right? So these things we will study. We will start studying these in the next class. And once we complete this, this particular chapter, very important and interesting one, will be completed, and then we will go into SQL. Okay. So today I will end it here. And next day we will start from normalization. We will continue normalization. We will end with all examples, and then we will go into SQL. Fine. So today I will end the class here. Thank you for attending. See you in the next class.